Hello, can you hear me? Can you see me properly? Yeah, Neeraj, I will answer this question at the end. At the end, I'll throw it open for questions. Of course, in the middle, also people can ask. But is the audio and video okay? Oh, great. Thank you. Let's wait for people to join. It's 2 minutes more to go for 7 o'clock. Okay, people haven't joined in yet. Let's wait. Funny. Nobody has joined yet. Although there are some 200 plus followers on Instagram and some 80 plus people on the WhatsApp channel. I think we'll wait 15 minutes. If nobody joins, then I will end it. Hello, yeah, Shaheri. We will be talking of all the three laws of Newton. I'm just giving 5 minutes time to for people to join in, Shahir. So 2 more minutes I'll wait, then we will start. So on this chat box, post your doubts, okay, as we speak. Now I can't see the chat box while I am showing my blackboard and all those. I can't see. So what I will do is that every 10 or 15 minutes, I will stop that and get into this chat box to see the questions and then I'll answer them. Okay. So Shahidi, can you see me and hear me clearly? Okay. So I'll wait 1 more minute. Shahidi, this is a live lecture on Newton's laws of motion. I'm just going to start. 1 minute. I'm just giving 5 grace minutes so that people can join. They're supposed to start at 7. I'm just giving 5 more minutes. Okay, let's begin. Um, I hope you can see the screen. So, the topic today is Newton's laws of motion. This is one of the most fundamental topics in all of mechanics. If we don't understand this chapter, then we cannot do anything in mechanics. So, it is so fundamental and it is beautiful. So, the agenda of this is that we will do a quick recap of the theory, force, momentum, and the three laws of Newton. Just a recap. And then we will go on to understand the methodology involved in solving problems, how to solve problems. We must understand that first, and then we will look at problems, and many of them are very, very interesting. Okay. So, a lot of people tell me, a lot of children tell me that they have understood the concept, but they are not able to solve problems. That could be due to many reasons. But one of the reasons is that they have not understood the concept itself. So that's very important to understand. So, what causes motion or what causes a change in motion? There's a football, somebody kicks it, and the football starts. The velocity was zero, now it acquires a certain velocity due to the kick. If there was no kick, the football would not start on its own. Then this baseball batsman hits the ball and turns it in another direction. The speed may not change, but the direction has changed, so the velocity has changed. Or a drop of water falls off the leaf, its velocity changes. Or a heavy box is being pulled using a rope. In all these cases, the velocity is changing. Either the speed is changing, or the direction is changing, or both. So, the cause of all motion, or the cause of all change in motion, is what we call force. It is force that causes motion or causes change in motion. It causes a change in velocity. So if it is change in velocity, that means force causes acceleration. So what is force? We define it by what it does. So it is that physical cause which changes or tends to change the state of rest of a body, makes it move, like the kick to the football, or the state of uniform motion like the hit by the baseball batsman, or even the shape and size of the body. Why did I say tends to change? Because it may not change. I'll take this example: somebody pushing a wall, the wall does not move. The man is exerting a force, but the wall does not move because there are other forces that are preventing. But the man is exerting a force. He is tending to change the state of rest or of state of uniform motion. So force is a push or a pull. It is a vector quantity. It has got a magnitude and direction, and the unit is called Newton. So a body at rest will continue to be at rest. A body moving with a certain velocity will continue to move with the same velocity unless there is a force on it, unless it is acted upon by a force. And this force should be external to the body. A living person, for example, can exert a force using his hands and legs, right? But there must be an external force for him to move. Internally, he can do whatever he wants, but that will not succeed. Okay. So let's look at some contact forces. Friction opposes motion. When you hang a ball from a string, there's a tension in the string. When a book is lying on the table is exerting a force called the normal reaction. When you elongate a spring, then the spring exerts a force inwards. When two cars collide, then there's a force during collision. These are all contact forces. But there are non contact forces as well. Let's look at, I'm just recapitulating actually. Effects of a force: it can change state of rest or of uniform motion, or it can change the size or shape. For example, it can start or stop a motion by kicking this football, or it can change the velocity of a cricket ball by hitting. Look at this. It can change the size. If you compress a balloon on all sides, it becomes a smaller balloon. The size has changed, the shape has not changed. If you can take a can of Pepsi and crush it, so force can do all of this. When you talk of starting or stopping a motion, let's take some cases, four cases, right? The velocity of a body is something already, and the force is in the same direction. The speed will increase because the force will tend to push it forward. It's like this boatman. He is pushing the oar backward, and the water exerts a force forward, so the speed increases. The speed increases, there is no change in direction. Suppose the force is opposite to the velocity, then the speed decreases, there is no change in direction, like friction. A body that is moving eventually stops due to friction. What happens if a force is perpendicular to the velocity at all times? The speed cannot change, but the direction will change. For example, if you tie a stone to a string to your finger, the stone goes around in a circle at a constant speed, but the direction of the speed keeps on changing. In general, the force may be at some angle to the velocity. Then this component, the parallel component, will increase the velocity, and this one will change the direction. So in this case, both speed and direction are changing. In each case, there is a change in velocity. So guys, force causes acceleration. Change in velocity means acceleration. Look at the changing of size or shape. If you hang a mass to a spring, the spring elongates, so the size has changed. If you take an iron rod and pull it in both directions, it elongates by some amount, so again it has changed. Or balloon can be compressed, or a gas can be compressed, the volume changes. So it can change the size or shape of a body. So what is Newton's first law then? Every body continues to be in a state of rest or a uniform motion in a straight line. This means uniform motion in a straight line means constant velocity, not constant speed, unless acted upon by an external force. This is very important. A lot of people make a mistake on this. External force. In other words, the acceleration of a body will be zero if and only if the net external force, this summation means net external force is zero. If the net external force is non-zero, then there will be an acceleration in the direction of the net force. So a body at rest is, suppose is said to be in equilibrium, called static equilibrium because it's not moving. A body moving with a constant velocity is also in equilibrium. Guys, a body moving with a constant velocity is also in equilibrium because there is no acceleration. Constant velocity, no acceleration. No acceleration means no net force. That is also called equilibrium. It's called dynamic. They are both unaccelerated. So that is the meaning of equilibrium. So force causes change in velocity, force causes acceleration. And inertia is a term used to say that how much resistance to change it is offering. Every body opposes a change in state. For example, greater mass will oppose a change more. A big rock is harder to move than a small stone. The mass itself is a measure of inertia. First law is also called law of inertia. But word of caution, inertia is only this much. Don't try to bring in inertia in everything, and you will see an example of that, where people tend to bring inertia into everything. Let's look at a question now from NCRT, Standard 10. A small spaceship is accelerating in interstellar space at a constant rate A. An astronaut inside the spaceship accidentally gets separated from it. What is the acceleration of the astronaut immediately after this instant? Assume there are no nearby stars to exert any appreciable force on it. So, there was a spacecraft, it was moving with some acceleration. There was an astronaut inside, he was also moving with the same acceleration. If he jumps out, if he gets separated, then what happens to the acceleration? As soon as he jumps out or gets separated, there's no force on him. Acceleration changes immediately. Force becomes zero instantly. Acceleration also goes to zero instantly. But the velocity can't go to zero instantly. See, it was going with some velocity. The man was also going with the same velocity. When he separates, he has that velocity. That doesn't change instantaneously. Because if it were to go to zero or something instantaneously, then the acceleration should be infinite. The acceleration is the change in velocity divided by the time taken. If this time taken is zero, then acceleration goes to infinity. That can't happen because force can't be infinite, right? Okay, so let me just take a break and see, are there any questions? Okay, no questions, so let's proceed further. Now let's look at the concept of momentum. Suppose two people are running with nearly the same speed, but one guy is fatter. And I ask you to stop both of them. Who is more difficult to stop? The speed is the same. Who is more difficult to stop? The fat man. The force that you need to exert to stop a fat man is will be large. So mass has got something to do with the required force. If I take another example, Usain Bolt running versus walking. When is he more difficult to stop? When he is running. So that means the required force depends on the velocity. Third example, a man is stuck in a building on fire and he has to jump out. So if he jumps out onto concrete, he will break his leg. But if he jumps out on a mound of sand, he does not break his leg. Why? Because the sand yields, it allows the foot to go inside, giving greater time to the leg to stop. Greater time. So greater the time, lesser is the force exerted by the body. Therefore, the leg doesn't break. You'll see this in cricket also. If somebody catches a ball, he has to pull his hand like this so that there is some extra time given for the ball to stop. If he just keeps his hand like this, the ball will come and jump out, right? So this mass, velocity, and time, bringing it together, the force is proportional to mass into velocity divided by time. And this is called momentum, mass into velocity. Linear momentum is mass into velocity. It is a vector and it's written as P. It is equal to mv. That is the momentum of a body. The direction of this momentum is the same as the direction of the velocity, right? So now let's come to second law of motion. The second law says that the rate of change of momentum of a body is directly proportional to the applied external force. Rate of change means what? Change is delta p. Rate of change means per second. That means delta t. Delta p by delta t is the rate of change of momentum, and that is proportional to the external applied force. So we write it like this. The proportionality constant turns out to be 1. So delta p is what? Delta of mv. But mass can change also, or velocity can change. So the rule in calculus is take the first function and then write the change of the second quantity. Then take the second function and then write the change in the first quantity. This is what is new. This is what is second law. This is what is second law. Don't ever make a mistake of saying that F equal to ma is second law. It turns out to be F equal to ma. If the mass is constant, then there is no change in the mass. So delta m is 0, right? Delta m is 0. 1 minute, somebody is messaging me. If the mass is constant, then this term vanishes. It is m into delta v upon delta t, and that is called acceleration. So we normally say F equal to ma, but strictly speaking, that is not the second law of motion. But in 95% cases, the mass is constant. So yeah, F equal to ma. Now this F equal to ma can be applied along any direction. Along x-axis, take the x component of the force mass into x component of the acceleration. Similarly for y and for z. So mass is not merely the quantity of matter within a body. It is the characteristic that determines the acceleration of a body under the action of a force. Okay. Let me just talk a little bit about a scenario where the mass is changing. The rocket is moving. It is ejecting gases. That is why it is moving, by the way. Since its mass is changing, then we cannot ignore the second term here. The mass is changing, so that force was equal to m delta v by delta t plus v delta m by delta t plus v delta m by delta t. Now this second term is not 0 because mass is changing. So we need to take care of both these terms. Suppose I take a special case that the speed is constant, velocity is constant, then this term goes to 0, right? Then the force on the rocket is simply the second term, v delta m by delta t. And delta m is negative because mass is reducing. So this force is also negative. The force acting on this rocket is like this. Okay. So the other quantity that you need to know is impulse. This is Newton's second law. If you take delta t that side, F delta t is delta p. F delta t is called impulse. So impulse is equal to change in momentum. Impulse is also a vector. Change in momentum is also a vector, right? So let me show this example of a bouncing body. When it hits this ground, it is changing its direction. Suppose I assume that the speed does not change, then the velocity is changing direction. So what is the initial momentum? The velocity is downwards, so initial momentum is downwards. What is the final momentum? Upwards. The magnitudes of them is the same, but the directions are different. And we will give a sign convention now. Any downward vector will say minus, any upward vector will say plus. So what is the change? Change in momentum is final minus initial. Final is plus mv. This is plus mv upwards minus the initial momentum, that is minus mv. So that becomes plus 2 mv. That is the change in momentum, and that is also the impulse. So, guys, the impulse acting on this body at when it collides is upwards, and its magnitude is 2 times mass into the speed. That is impulse. All right. So now let's talk about the steps in solving problems. This is very important. Please Please pay close attention. People have a problem in solving problems because they do not follow the appropriate steps. So, first thing is read the question. That sounds obvious, but people don't read, don't understand. And quite often, drawing a diagram helps. Read it properly. Second step, conceptualize. That is, what concepts should be applied. Is there an external force or internal force? Is the mass constant, mass constant? So, what concept should we apply? Not what formula that we should apply. Definitely, we should conceptualize, but not formalize, if there is such a word. Set up equations between known and unknown and then solve. Sounds very simple, but people don't follow these steps. This applies to any problem. Now, specifically with Newton's laws of motion, we have a method to solve also. In addition to this, is called free body diagram. What is the free body diagram? Free body diagram means take the body and free it from others and draw only the forces acting on the body. Only draw the forces acting on the body. Don't show those forces that this body exerts on others. Then decide the axis, set up equations, and solve. Let me take an example of drawing a free body diagram or FBD. A boy is holding a book, supporting a book on his head, and both are at rest. Draw the FBDs of the boy and the book, right? Both are at rest means net force is zero on each one of them. So if I look at the book, this is the book. His mass is m, so the weight is mg, and he's at rest, so there must be an upward force equal to mg, right? Sorry, I'm talking about the book, right? So it is like this: the boy and the book, right? So I'm talking about the book right now. So this normal reaction is being exerted by the boy, and these two are equal in magnitude. Therefore, the book is at rest. What about the boy? His own mass is capital M, so his weight is mg, and the ground is exerting force on the boy. The ground is exerting a force. I'm calling it n dashed, so that is upwards. Now, the book's weight is acting on his head now, and the book's weight is mg, but mg is equal to n, so that n is by the book, right? So we can say that the downward force n plus n dashed, the downward force is n and mg, n plus mg is equal to n dashed because net force should be zero. Okay, so let us do the first question on impulse from NCRT. A batsman hits a ball straight towards the bowler without changing the speed. The speed was 12 meters per second, right? The mass of the ball is given. Determine the impulse. Impulse is change in momentum, but momentum is a vector. So, what is the initial vector? The mass was going at 12 meter per second, returns along the same direction but opposite. The speed does not change. So, what is the initial momentum? Momentum initially is like this, and that is treated positive plus mv. The mass is 0.15, uh, not gram, it is kg actually, 0.15 kg, and the speed is 12, so 1.8. And momentum is mass into velocity. Just 1 minute. Momentum is mass into velocity, so kg into meter per second plus. And final momentum is this way, that is minus mv, same value. What is the change? Final minus initial. Final is minus 1.8 and initial is plus 1.8. So the whole thing is minus 3.6 kg meter per second. That is the impulse. And the impulse is this way, right? Impulse is along the change momentum vector. Clear? This is fairly easy. Another fairly easy question. A bullet of some mass moving with some speed enters a heavy wooden block and is stopped after covering a distance of so much within the block. What is the average resistive force on the bullet by the block. So we can first of all draw a small diagram. Bullet is coming with a speed u and a mass m. Here the final speed becomes 0, and it covers a certain distance here, right? So if I apply this one, this I'm assuming that the force is constant. So v square equal to u square plus 2as, v is 0, and we just write it. So a is minus u square by 2s. This will go that side, minus u square by 2s. This is a. So the force is, the minus implies that it is opposite to the, uh, I mean, this vector is treated positive. Any vector this way will be treated negative as per the sign convention. So minus means acceleration is to the left, force is also to the left. The magnitude of the force, therefore, is m into a, which is minus u square by 2s. So the magnitude, this means magnitude. M u square by 2s. M is 0.04 kg. U is 90, so u square. Divide by 2 into the s is 60 centimeter. Convert that to meters in SI units. Some calculation, it gives us 270 newtons. Okay. Alternately, we can solve by another method. What is the average velocity in this journey? Well, that is initial plus final divided by 2. So u by 2. U plus 0 by 2. 90 by 2, 45 meter per second. So the time taken for it to stop is distance divided by the average speed. Distance is zero point 0.6 divided by 45. That is the time taken. So the force is change in momentum divided by the time taken. And change in momentum was mass into velocity. And this is a magnitude rather, right? And delta t is zero point 0.6 upon 45. We get the same answer. Is this clear? Let me check. Let me check the chat box. Any doubts? Okay, looks like nobody has doubts. I'm just waiting for a minute. Any doubts? Now we'll see some very interesting questions. This is what we did. Now, guys, how do we explain this? How does a jumper jump up? I mean, for any motion to happen, there should be an external force. This person is jumping up. There should be an upward force, no? Who is exerting that upward force? And how is that force getting exerted? Other one, how does a boat move forward? The boat doesn't have any engine, etc. How does it move forward? And how does a man climb up on a rope? Which force is responsible for pushing this man up the rope? Finally, how does a helicopter hover in air? Who's supporting the weight of the helicopter? In all these cases, if I just go back, this jumper is pushing the ground downward. The ground pushes the jumper upward. If I look at the boatman pushes the oar backward. The oar is pushing the water backward. The water pushes the oar and therefore the boat forward. The man pulls the rope downward and the rope pushes him upward. Then the helicopter, the rotor is pushing the air down and therefore the air exerts a force on the helicopter. This is Newton's third law. For every action, there is an equal and opposite reaction. I just want to mention that this is not a perfect way of saying things, but at 10th standard, it is okay. When you come to 11th, I will tell you the right way to talk of Newton's third law. Because here the question is who's acting, who's reacting, right? How do you decide that? So, anyway, at this level, third law is this. And these forces occur in pairs. They are called Newtonian action reaction pairs. For example, two bodies A and B, suppose they're attracting each other. So this is force by B on A attractive. This is the force by A on B attractive. These two forces are equal and opposite. So vectorially, I'll say FAB is equal to minus FBA, meaning they are opposite to each other, right? Do they cancel out each other? That's a very important question. Another example, laptop on the table, the weight acting downward and the normal reaction is equal and opposite by the table. And sun attracts the earth. Equally, earth attracts the sun by gravity. Do they cancel out each other? They don't cancel out each other because they're acting on different bodies, right? But if I consider, let us say, two bodies as my system, then these forces are canceling out. So that means if I define a set of two or three or four bodies as a system, and I find these guys are exerting a force on each other, equal and opposite, then the net force on the system externally is zero. There are a lot of internal forces, but externally the force is zero. And that word is very important, external. We'll see an example. Here is the example. Tell me the answer. You can see horse and cart going together. But my doubt is this. How does the whole system of horse plus cart move forward? You will say horse is pulling the cart. I will say cart is equally pulling the horse backwards. No, right? Newton's third law. So how is the system moving forward? Any answers? Let's make it interactive, guys. Please type in your answers. I want to see. Type in your answers. What makes the whole thing move forward? The horse and cart. Well, nobody. Here is the answer. It is the ground that is coming into the picture. Look at the horse's legs. The horse pushes the ground backward. This is the force by the horse on the ground. The ground reacts by exerting an equal and opposite force on the horse. Therefore, the whole thing moves. There should be an external force on the system to make the system move forward. Internal forces cannot make a whole system move. Okay. Now, on the same topic, look at this drowning man. Can he save himself by pulling his left hand with his right hand like this? Hold his left hand and pull it with his right hand. Can he pull himself up the water and save himself by pulling his own left hand with his own right hand? Is that possible? What do you think? Well, this is not possible because man is one system, right? He has got a left hand and a right hand, of course. But if he pulls his left hand with his right hand with a certain force, the left hand equally pulls him down. So on the man as a whole, on the system as a whole, there is no external force. External force is required to cause a motion. Yes, he can be saved in this manner. Someone else pulls his hand. That force is external to the whole system. Then only he can save himself. This is where people make a mistake. Okay. Uh, Very simple question from ICSE. Use of F equal to ma. A ball of some mass is going with some velocity. It is brought to rest by applying a resistive force and it travels 5 meters before stopping. What is the retardation caused by the force? Retardation means negative acceleration. And what is the force? Well, we can apply kinematics here. Given mass, initial velocity, and the distance traveled, and final velocity is zero. This is given. So if I apply V is equal to U square plus 2as, V is 0, U is 10 meter per second square, acceleration is unknown, but S is 5. So from here, A is this 10 square comes here as minus 100, and this is 2 into 5, 10. So A is minus 100 by 10, that is minus 10 meter per second square. Minus implies retardation. So the magnitude of the force is mass into acceleration. Mass is 100 gram. Convert that to kg. You have to use SI units at all times. And A was 10, so 1 Newton. Simple, very simple. Another very simple question from ICSE. A ball of some mass initially at rest, so U equal to 0, initial velocity equal to 0, and there's a force of 10 kgf. Now, what is kgf? Kgf, 1 kgf is weight of 1 kg mass. And weight is mass into g. So that'll be 1, and g is 9.8, but I'll take g as 10 as given. So 1 into 10, so that is 10 Newton. 1 kgf is 10 Newton. And that force acts for 10 seconds. What is the acceleration? What is the velocity acquired? And what is the distance traveled? Well, given, sorry, given mass, initial velocity, time for which the force acts, and the force itself is 10 kgf. I beg your pardon. This was 10 kgf. 1 kgf is 10. So 10 kgf is 100 newtons. This was given. So what is A? Force by mass. Force is 100 newtons. Mass is how much? 0.5 kg. We get 200 meter per second square. Then velocity, u plus at, u is 0. A is how much? 200. A is 200, and time given is t. So 2000 meter per second. What is the distance traveled? S equal to ut plus half at square. U is 0, so half at square. A is 200 and time is 10. We get 10,000 meters. Right. These are extremely simple questions, and I hope you don't have a problem with all of this. But this is a little bit thinking from ICSE. A rocket is moving at a constant speed in space by burning its fuel, but the speed is constant, and ejecting out the burnt gases through a nozzle. Is there a change in momentum? If yes, what causes the change? The speed is constant, let's say direction is also constant, so velocity is constant, but the mass is reducing, so momentum is reducing, right? Momentum is reducing. So, who is responsible for that? Well, there is a backward force, maybe due to the fact that it is not in space, it is still within the atmosphere, the air resistance. There must be some force which is opposing that, right? Another ICSE question, very simple. Two balls are there whose masses are the ratio 1:2. They are dropped from the same height. What is the ratio between the velocities when they strike the ground? Will the heavier mass hit the ground with a greater velocity or lesser velocity? And what is the ratio of the forces acting on them? So one mass is, let us say, m, the other mass will be twice. They are dropped from the same height. But when they are dropped, both of them have the same acceleration, which is acceleration due to gravity called g, and that is downwards. So since the acceleration is the same and the initial velocity of both of them was the same, therefore, if I apply the v equal to u square plus 2as, they will have the same velocity. So the ratio will be 1:1 of the velocities. What is the ratio of the forces? Since force equal to mg, F1 by F2 will be equal to the mg of the first and mg of the second. Gg cancels, cancels, 1:2, right? Very interesting. Although the force is different, the acceleration is the same. Why? Because the masses are different. Okay. Another simple question. A car of mass 600 kg is moving with this speed, while a scooter of some other mass is moving with some other speed. Compare their momenta. Momenta is a plural of momentum. Which vehicle will require more force to stop in the same interval of time? So first, let's calculate the momentum for a car, mv. M is 600 kg, V is 10 meters, so 6000 kg meter per second. Scooter, mass is 80 kg, speed is higher, so 4000. Which is larger? Car. So if I take the ratio of the car and scooter momentum magnitude, 6000 by 4000 is 3 by 2, 3 is to 2. Now, which vehicle will require more force? Now, you see, the time is the same. So, F equal to delta P by delta T. But delta T is the same. So, the force is proportional to the change in momentum. The final momentum of both the guys has to be zero because they are stopping, right? So the change in momentum for the car is larger. Therefore, the car will be harder to stop in the same interval of time than the scooter. Another simple question, same force, different masses. Two bodies have masses at ratio 3 is to 4. When a force is applied on the first body, it has this acceleration. How much acceleration will be caused on the second body? Well, same force, right? Same force. So M1 A1 will be equal to M2 A2. So A2 is M1 A1 upon M1 A1 upon M2. So M1 by M2 is how much? 3 by 4. So that becomes 4.5 meter per second square. Since the mass of the second guy is larger, the acceleration has to be smaller for the same force. Now I talked of inertia. Look at this experiment. There's a coin on a cardboard and the cardboard is on a glass. Somebody gives a sharp impulse onto the cardboard, so the cardboard flies away, and the coin falls into the glass. People say because the coin has inertia. Everybody has got inertia, but this experimental result is not due to inertia. It is due to insufficient friction. See here, let me explain. I have my phone here, right? I have my phone here and I keep an object on it. I'm keeping an object on it. This is an eraser. All right, you can see phone and eraser. Both are at rest. If I start moving the phone, the eraser is moving along with the phone. But I'm not touching the eraser, no. I'm not touching it. Then who's exerting the force on the eraser that it is moving? Nothing can move without a force. Who's exerting? Certainly I am not exerting because I'm not even touching it. It is the phone that is exerting, and that is the friction between the two that is carrying them together. Okay, so friction is sufficient for both of them to carry forward. But if I accelerate my phone very quickly, like this, then the eraser does not go together because the friction is not sufficient. Friction has got a problem. Friction cannot be unlimited. There's a limiting value of the friction. So that is the issue. So don't take inertia too seriously. Okay, let's talk of tension in a string. So if a bob is hanging and we have a string, then if I look at the bob, the weight is acting downwards, the tension must be acting upwards, and the tension is equal to mg. Tension is a pulling force, not a pushing force. See, I can tie a rope to a person's hand and pull him, right? But I can't push with the string. Tension cannot push, tension can only pull. Therefore, the tension, wherever we are showing, the tension must be shown acting away from the body. At the ceiling, the tension is pulling the ceiling and it is a pulling force, so it should be shown like this. Okay. So if the mass of the string is very small, negligible, then the tension is the same everywhere. So let us consider that scenario. I'm not getting into a more complicated scenario. Okay, here is the question, and I would like you to tell me the answer. There's a 2 kg mass connected to a 1 kg mass by a string, and a force of 30 Newton is applied on the 2 kg mass. As a result, both of them move together with the same acceleration. then what is the tension in the string? Or the tension here will act like this, the tension here will act like this. What is the magnitude of the tension? And suppose we reverse the scenario that we apply the 30 Newton force on the 1 kg mass, then is the tension same or different? Does the tension depend on how it is pulled? Can you give me at least the answer for the first part? That the force is on the 13, the force of 30 Newton is applied on the 2 kg mass, and we have to find the tension in the string. Post your answers on the chat box. Okay, the answer is 10. See here, if I look at the 1 kg mass, it is also going with the same acceleration, right? So this acceleration I can find out. The net force is 30 Newton. The net external force, that is important. This tension is internal to the system, right? External force is 30 Newton and the mass is 2 plus 1, 3 kg, right? So acceleration is 10 meter per second square. So if I look at the free body diagram of the 1 kg mass, this is 1 kg mass, the tension is pulling it to create an acceleration of 10 meter per second square. Therefore, the tension should be the mass into the acceleration, that is 10 newtons. So here the answer is 10 newtons. But here it is the same acceleration, which is 10 meter per second square. Same acceleration. But this tension is pulling the 2 kg mass. So now the tension will be 2 times 10, 20. That is an interesting question. So see here, another interesting question. There's a monkey of some mass m and a bunch of banana of the same mass and connected by a long rope over the pulley, very long rope. And this distance is 2 meters. The monkey thinks that he can get the banana by climbing up. So he climbs up. He climbs up the rope with a speed of 1 meter per second. After how much time will he reach the banana? People will say, oh, 2 meters. And he's going at 1 meter per second, so 2 seconds and go. I'm saying after a long time. Why? Because if he pulls the rope, right, he is going up, right? So there is a force by the rope on the monkey, and the monkey was pulling the rope downwards with the same force, right? So if he is pulling the rope with a certain force, this force will cause a tension all the way, and this mass, this banana will also go up by the same distance as the monkey goes up. So the separation between the monkey and banana will never reduce, except when the banana reaches right here and then it gets stuck and then the monkey can go and catch. So that's why I'm saying after a long time, right? Finally, weight is mg, is a non-contact force. And if you look at the weighing machine does not read mg, it reads the n that it is exerting on the body, right? So can this happen? That there's an elephant standing on a plank and a person is supporting the entire weight and the person is smiling. Is it possible? It is possible. If everybody is falling freely, a freely falling body is weightless. A freely falling body is weightless. so is a floating body. Concept of weight. So we end this session by just talking a little bit about the validity of Newton's laws of motion. Are they always valid? No, they are not always valid. Newton's laws of motion are called classical mechanics. So if I talk of the speed of a particle versus and the size of a particle, if the speed is very small compared to the speed of light and the size is greater than 1 nanometer, like a dust particle or a drop of water, all that is fine. Then Newton's laws of motion is fine. But suppose the speed is high, the size remains the same for a piece of rock, let's say. The size is the same, but the speed is very high. Let's say 20% of the speed of light. Then we cannot use Newton's laws. They are not valid. We have to use Einstein's theory of relativity. Similarly, if the speed is low, but the size becomes very small, then again we can't use Newton's laws of motion. We have to use quantum mechanics. And finally, if the speed is high and the size is low, then we have to use quantum field theory. So that is the end of the session. I hope you guys enjoyed it. Any questions? Final questions? No? All right. Thank you for attending.